All right, class, today we're going to explore how the invisible forces between molecules, called intermolecular forces, determine whether something is a solid, a liquid, or a gas, and why these states matter in nursing. These forces are the reason ice floats in your drink, why your sweat cools you down, and even why oxygen can dissolve in your blood. By the end of this lecture, you'll be able to explain how these forces impact patient care. For example, how humidity affects a patient's ability to cool down, or why certain IV fluids mix well while others don't. Here's our first key idea. Molecules are not floating around without any interaction. They actually feel each other through tiny attractions called intermolecular forces. Think of water in a drop on a leaf. The drop forms a round shape because water molecules pull on each other like friends holding hands. This is why the drop doesn't just spread out flat. In your nursing practice, this matters because many physiological fluids, blood, plasma, urine, behave in similar ways. The way molecules stick together influences how they move through vessels, how drugs dissolve, and how cells maintain shape. Clinical connection. Why should you care? For example, the surface tension caused by these forces in the tiny air sacs, alveoli, in your lungs is so strong that without a substance called surfactant, those sacs could collapse, making breathing nearly impossible. This is a key point in premature infants, who often lack enough surfactant and develop respiratory distress syndrome. Let's zoom out for the big picture. Molecules don't live alone. They attract each other with intermolecular forces, tiny pulls that are weaker than covalent or ionic bonds, but strong enough to decide whether a substance is a gas, liquid, or solid at room temp. In nursing terms, these forces help explain why water forms droplets, why your IV fluids behave the way they do, and why lungs need surfactant. Big message: the stronger the attractions between molecules, the stickier the substance, and the more likely it is to be liquid or solid rather than a gas. Think of a tug of war between intermolecular forces pulling molecules together and thermal energy jiggling them apart. When heat wins, molecules fly apart, more gas behavior. When attractions win, molecules huddle, liquid or solid behavior. Your clinical tie-in: fevers increase thermal energy, more evaporation from skin, affecting hydration status. You'll assess I and O's and mucous membranes more carefully in febrile patients. In liquids and solids, molecules are close together. Liquids close but mobile, like people in a crowded hallway who can still slip past each other. Solids, same crowd, but everyone's stuck to assigned spots, only vibrating. This matters for medication forms: syrups, liquids, pour and mix, tablets, solids must dissolve before absorption. As nurses, we anticipate onset differences based on the form. Quick contrast: gases are far apart, compressible, shape-filling. Liquids and solids are dense and not easily compressed. That's why oxygen tanks hold a lot of O2 under pressure, compressible gas, but a bag of normal saline isn't compressible. This also explains why air emboli can move and expand in the bloodstream, while a liquid bolus will not. Gases have low density, no fixed shape or volume, and very weak intermolecular forces compared with thermal energy. Classic example, CO2. That's why gases diffuse quickly across alveolar membranes. Liquids are denser than gases, take the container's shape but keep a fixed volume and aren't easily compressed. Their forces are moderate. Water is our gold standard example. Think IV bags. You can't squish them smaller. There's not much give. Solids are dense, keep shape and volume, and resist compression because their intermolecular forces are strong. Sugar crystals are a simple example. Solids can be crystalline, ordered, or amorphous, disordered, relevant to how some meds are formulated. Polymorphs can change dissolution. In liquids, molecules are free to slip past each other, so the fluid flows and takes the container's shape. That's why blood flows. It's not just thin, it's molecularly mobile. Clinically, we think about viscosity changes. For example, dehydration makes blood more viscous, slowing flow. In solids like ice, molecules are fixed at positions but still vibrate, so they're not frozen in time, just locked to a spot. That's why ice keeps its shape in a cup. Now, two feelable properties of liquids: surface tension, how tight the surface skin is, and viscosity, resistance to flow. Without intermolecular forces, matter would be all gas, no liquids, no solids. In healthcare, you see this as surfactant therapy in neonates, reducing alveolar surface tension, and as changes in blood viscosity with dehydration. Surface tension is why a carefully placed paperclip can float on water. The top layer acts like a stretched film. Gasoline can't do this because its intermolecular forces are weaker than water's. In the lungs, water's strong surface tension would collapse alveoli without surfactant to loosen that film. Here is a mini NCLEX check. A preterm infant has increased work of breathing, nasal flaring, and intercostal retractions. Which intervention targets the chemistry causing alveolar collapse? A. IV isotonic fluid bolus. B. Aerosolized surfactant administration. C. Nebulized epinephrine. D. Oral diuretics. The correct answer is B. Rationale: surfactant reduces surface tension, preventing alveolar collapse. Choices A, C, D don't address that mechanism. Visually, molecules at the surface feel a net inward pull, like kids on the edge of a huddle being pulled toward the group. That inward pull tightens the surface, giving us surface tension. Viscosity is how much a liquid resists flowing. Maple syrup crawls, water runs. More intermolecular attraction means higher viscosity, which leads to slower flow. Long chain-like molecules tangle and raise viscosity. Picture long spaghetti versus short rice. Nursing link: dehydration will result in higher blood viscosity, which leads to sluggish perfusion. You'll watch capillary refill, mental status, and urine output. Here's that maple syrup image again. Stronger molecular interactions mean the liquid can't slide as easily. Translate to practice. Cold liquids are typically more viscous. Warming IV fluids, when appropriate and per policy, can reduce resistance through lines. Liquids can slowly turn into gases even without boiling. That's evaporation. The rate depends on three things: more surface area, higher temperature, and weaker intermolecular forces. Volatile liquids like alcohol evaporate quickly. Non-volatile liquids like syrup don't. Clinically, think about alcohol-based skin preps. They evaporate fast, cooling the skin and leaving behind a dry surface for injections. Or why fever can worsen dehydration: more body water evaporates through the skin and lungs. Molecules at the surface of a liquid are held less tightly than those inside. If they have enough kinetic energy, they can escape into the air. That's evaporation. In nursing, that's the chemistry behind how sweat cools you. The fastest, most energetic water molecules leave your skin, taking heat with them. Key: this is a physical change. No chemical bonds in the molecules themselves are broken. At any given temperature, not all molecules move at the same speed. They have a distribution of energies. Only a few have enough to escape. Raise the temperature and more molecules have enough oomph to vaporize. That's why a fevered patient loses fluids faster. Higher temp means more evaporation. Condensation is the reverse. Gas molecules lose enough energy to stick together into a liquid. You see this clinically when humidified oxygen delivery prevents airway drying. Moisture condenses inside tubing or on the mask. In a closed system, evaporation and condensation eventually balance out, called dynamic equilibrium, and the vapor pressure stabilizes. Vapor pressure is the pressure of vapor molecules in equilibrium with their liquid. It increases when temperature goes up or when intermolecular forces are weaker. Clinical angle: high vapor pressure means more easily inhaled vapors. That's why volatile anesthetics are stored in temperature-controlled vaporizers. When a liquid is in a closed container, molecules are constantly leaving the surface, evaporation, and returning from the gas phase, condensation. Eventually, those two rates balance, dynamic equilibrium, and the gas above the liquid exerts a specific pressure called the vapor pressure of that liquid at that temperature. It's the partial pressure of the liquid's vapor when evaporation and condensation are equal. Two testable takeaways for nurses. Temperature rules. Raise the temperature, more energetic molecules, higher vapor pressure. Substances with weaker intermolecular forces also have higher vapor pressure because it's easier for molecules to escape. Think alcohol preps. They evaporate readily, high vapor pressure, and feel cool on skin. Surface area doesn't change the final vapor pressure. Spreading the same liquid into a shallow tray versus a narrow beaker does not change the equilibrium vapor pressure. Bigger surface area speeds up how fast equilibrium is reached. Both evaporation and condensation speed up equally, but the final vapor pressure at that temperature is the same. Clinical connection. Humidified oxygen vent circuits, larger reservoir surface area brings the system to its target humidity, equilibrium, faster, but the final moisture content linked to vapor pressure at that temperature is determined by temperature and the liquid's properties, not surface area. Volatile agents, solvents, high vapor pressure liquids, alcohols, some topical solvents, volatile anesthetics, and controlled devices evaporate readily, great for fast skin prep drying, but it also means stronger fumes and fire risk near cautery. Storage and temperature control matter. Quick check. If I pour 20 ml of isopropyl alcohol into a wide tray and the same amount into a narrow beaker, then cap both at the same temperature, which one will have the higher vapor pressure at equilibrium? Answer: neither, both are the same. The tray just reaches equilibrium faster because of the larger surface area, but the equilibrium vapor pressure depends on temperature and the liquid's intermolecular forces, not surface area. Boiling happens when vapor pressure inside the liquid equals atmospheric pressure. Bubbles form throughout the liquid, not just at the surface. At higher altitudes, atmospheric pressure is lower, so liquids boil at lower temperatures. Clinically, this matters for sterilization. Boiling point changes can affect how well pathogens are killed if you're working in a low-pressure environment. When you heat a liquid to its boiling point, extra heat doesn't raise the temperature. It's used to break intermolecular forces so molecules can escape into the gas phase. That's why boiling water stays at 100 degrees Celsius at 1 atm until it's all steam. In patient care, that's the principle behind temperature plateaus when ice melts or liquids boil. The energy is going into phase change, not temperature change. This graph shows water warming from room temp through boiling. Notice the flat line during boiling. That's where added energy goes into vaporization, not heating. The same happens at melting points. Remember, in phase changes, temperature stays constant until the change is complete. When sweat evaporates, it's endothermic. It absorbs heat from your skin. This is a natural cooling system, but it's less effective in high humidity because the air is already saturated with water vapor, slowing evaporation. In high humidity heat waves, you'll see more heat exhaustion or heat stroke because the chemistry of evaporation is blocked. Mini NCLEX style question. A runner collapses after a race in high humidity. Skin is hot and moist, temp 40.2 degrees Celsius. Which chemical principle best explains why sweating failed to cool the patient? A. Increased intermolecular forces in sweat prevented evaporation. B. High atmospheric water vapor reduced the rate of evaporation. C. Sweat molecules had too little thermal energy at high temp. D. Boiling point of sweat was higher than body temperature. Correct answer, B. Rationale: high humidity means the surrounding air already contains many water molecules, reducing the evaporation rate, limiting cooling. Condensation is exothermic. It releases heat. Imagine steam from a kettle hitting your skin. It burns more than boiling water because the steam is giving up extra heat as it condenses. In patient care, this is important when using humidified oxygen. If condensation forms in tubing, it can drip into devices, and the heat release isn't the main concern, but you'll know the process involved a release of thermal energy. The heat of vaporization, delta H vap, is how much energy you need to vaporize 1 mole of liquid at its boiling point. For water at 100 degrees Celsius, delta H vap is 40.7 kilojoules per mole. Positive for evaporation, endothermic, negative for condensation, exothermic. In clinical thermoregulation, this large heat requirement is why sweating can remove so much heat from the body. You're using that 40.7 kilojoules per mole to break molecules free. You can use delta HVAP to figure out how much heat is needed to vaporize a given mass of water, or, working backward, how much water could be vaporized by a given heat input. Clinical example, estimating fluid loss from fever and high respiratory rate. You may not plug in these equations at the bedside, but you're applying the principle when you anticipate dehydration risk. This slide's data table reinforces that water's delta HVAP is high compared to many liquids. That's why it's such an effective coolant. Nursing tie-in, When patients lose water through evaporation, such as fever, burns, or rapid respirations, they're also losing large amounts of heat. With burns, though, that heat loss isn't helpful. It can contribute to hypothermia. Here is an example. If you have 155 kilojoules of energy, how much water could you vaporize at 100 degrees Celsius? Step 1, divide energy by delta HVAP. 155 kilojoules divided by 40.7 kJ per mole equals approximately 3.81 moles. Step 2, convert moles to grams. 3.81 moles times 18.02 grams per mole equals approximately 68.6 grams of water. So 69 grams of water, which is a little over 2 ounces, could be turned into steam with that energy. Point is, evaporation moves a lot of energy with even small amounts of water. Here the problem is reversed. You're given a mass of water and asked for heat needed. In nursing, the parallel is calculating IV fluid replacement for insensible losses, except we measure in ml and liters, not moles, but the chemistry is the same. When you melt a solid, molecules gain enough thermal energy to break free from fixed positions, but still stay close together in liquid form. Melting is endothermic, it absorbs heat like ice cooling a drink. Freezing is exothermic, it releases heat. Your freezer has to remove that heat to keep freezing going. In healthcare, freezing injury, frostbite happens because ice inside cells expands and ruptures them. Conversely, melting ice in contact with skin pulls heat away, risking hypothermia. Mini NCLEX style question. A patient with heat stroke is cooled by placing ice packs in the axillae and groin. From a chemistry perspective, why is melting ice effective at lowering body temperature? A. It releases heat into the body. B. It absorbs heat from the body to break molecular bonds. C. It decreases the body's vapor pressure. D. It lowers the body's boiling point. Correct answer, B. Rationale, melting is endothermic. Energy, heat from the patient's body is absorbed to overcome the solid's intermolecular forces, lowering body temperature. When ice melts into water, the temperature stays at 0 degrees Celsius until all the ice is gone. Only then does heating raise the temperature of the liquid. This is why an ice slurry in a cooling blanket can keep a patient's temp steady for a while. The phase change locks the temp until the ice is melted. A heating curve shows temperature versus heat added. At the melting plateau, heat energy is going into breaking intermolecular forces, not raising temperature. This plateau at 0 degrees Celsius is constant for ice water mixtures under 1 atm pressure. When you drop ice into a drink, melting absorbs heat from the drink, cooling it. That's endothermic. Freezing works in reverse. As water solidifies, it releases heat. Clinically, frostbite injury happens partly because when ice crystals form inside tissues, the expansion ruptures cells. The heat release from freezing doesn't help. It's too localized and is outweighed by the structural damage. The heat of fusion, delta HFUS, is the amount of heat needed to melt 1 mole of solid at its melting point. For water, it's 6.02 kilojoules per mole. Positive for melting, endothermic, negative for freezing, exothermic. Clinically, knowing how much heat ice can absorb before becoming liquid helps in designing therapeutic hypothermia protocols. Ice baths can pull large amounts of heat without changing temperature until fully melted. This slide shows water's delta H fuse compared to other substances. Water's value is fairly high because hydrogen bonding holds molecules together tightly. That's why ice absorbs a lot of heat as it melts, helpful for cooling, but also why frozen foods take longer to thaw. Example, if 237 kilojoules of heat melts ice at 0 degrees Celsius, how much ice is that? Step 1, divide by delta H fuse. 237 kilojoules divided by 6.02 kilojoules per mole equals approximately 39.37 moles. Step 2, multiply by molar mass of water. 39.37 moles times 18.02 grams per mole equals approximately 710 grams. That's over 1.5 pounds of ice. In a clinical sense, these calculations explain why significant ice melt can remove enough heat to drop body temperature, important for hypothermia induction in post-cardiac arrest care. Skill Builder Connection. These math skills translate to patient care whenever you're estimating heat exchange, whether it's cooling hyperthermia, thawing frozen plasma for transfusion, or maintaining vaccine cold storage during transport. This heating curve shows ice from negative 25 degrees Celsius warming to steam at 125 degrees Celsius. You can see three main plateaus. At 0 degrees Celsius, melting, freezing. At 100 degrees Celsius, boiling, condensation. Between plateaus, added heat changes temperature. On plateaus, added heat changes phase. This visual is key for understanding why patients wrapped in ice packs won't cool below a certain point until the ice is melted. That's just how phase change thermodynamics works. Mini NCLEX style question. A patient in the ICU is undergoing targeted temperature management after cardiac arrest. Large ice packs are placed along the torso, which best explains why the patient's temperature plateaus around 0 degrees Celsius in the packs themselves until the ice is gone. A. Heat from the patient is being used to break hydrogen bonds in ice. B. The body is producing heat faster than ice can absorb it. C. Ice cannot absorb heat at temperatures below 0 degrees Celsius. D. The latent heat of fusion decreases with larger ice mass. Correct answer, A. Rationale: during melting, heat is used to overcome hydrogen bonding between water molecules and ice. Temperature doesn't rise until all ice is melted. Sublimation is when a solid turns directly into a gas without becoming a liquid first. A classic example is dry ice, solid CO2. At atmospheric pressure, CO2 never melts into liquid. At negative 78 degrees Celsius, it skips straight to gas. In healthcare, sublimation shows up in freeze-drying medications, lyophilization. Moisture is removed from the frozen drug under low pressure, causing ice to sublime into vapor. This preserves the drug for long-term storage without damaging heat-sensitive compounds. Dry ice is solid CO2, and because it sublimes rather than melts, it's perfect for shipping temperature-sensitive medical supplies. No liquid forms to leak or cause contamination. But safety note, CO2 vapor can displace oxygen in enclosed spaces, so you need proper ventilation. Regular ice also sublimes, even at freezer temperatures below 0 degrees Celsius. That's why ice cubes shrink over time in the freezer. They slowly lose water molecules into the freezer air, which may then redeposit elsewhere. This is the same chemistry that causes freezer burn on food. Water leaves the food structure and refreezes as ice crystals elsewhere. When frozen foods are stored too long, sublimation pulls moisture out, leaving them dried and tough. The ice you see in a frozen bag of veggies isn't from the freezer, it's from the food itself. In industrial food preservation, deep freezing reduces sublimation rates, keeping food texture intact longer. Now, let's connect all of this phase change behavior back to what's really in charge: the forces between molecules. There are three fundamental types. 1. Dispersion forces, which are the weakest, are present in all molecules and atoms. 2. Dipole-dipole forces, stronger, occur in polar molecules. And 3. Hydrogen bonds, the strongest of the three, occur when hydrogen is covalently bonded to F, O, or N and interacts with another highly electronegative atom. Rule of thumb: stronger intermolecular forces means higher melting point, higher boiling point, lower vapor pressure, and usually slower evaporation. Clinical angle: these forces affect drug solubility. Polar drugs dissolve better in polar solvents like water, and formulation stability. Freeze-dried meds rely on disruption of intermolecular forces during sublimation. Mini NCLEX style question. A nurse is preparing to reconstitute a freeze-dried antibiotic. The powder was created by removing water through sublimation. Why was sublimation used instead of simple evaporation? A. Sublimation allows removal of water without heating, preserving drug structure. B. Sublimation removes only surface water, leaving most water bound. C. Sublimation increases the drug's polarity, improving solubility. D. Sublimation makes the powder sterile without further processing. The correct answer is A. Rationale: freeze-drying uses sublimation at low temperatures and pressures to remove water without exposing heat-sensitive drugs to high temperatures that could degrade them. Dispersion forces, London forces. Dispersion forces are the default intermolecular force. They exist between all atoms and molecules, even nonpolar ones. They come from tiny temporary shifts in the electron cloud that create an instantaneous dipole, a quick, uneven distribution of charge. Because every atom has electrons, every atom can have these momentary dipoles. In nursing, why does this matter? Even nonpolar gases like oxygen can dissolve a little in blood plasma because of these weak attractions. And in medical plastics, dispersion forces between polymer chains influence flexibility and drug absorption. Picture a helium atom. Normally, its electrons are evenly spread, but at any moment they might be off balance, giving one side a slight negative charge and the other side a slight positive charge. That's an instantaneous dipole. Nearby atoms feel this shift and their electrons move in response, creating another dipole. That's how dispersion forces spread. These fleeting attractions are weak, but when you have lots of them, like in large molecules with big electron clouds, they add up. Clinical example, anesthetic gases. The bigger the molecule, the stronger the dispersion forces and the higher the boiling point. This affects how they're stored and vaporized for inhalation. The ease with which the electron cloud can shift is called polarizability. Larger atoms molecules mean bigger, looser electron clouds, which correspond to more polarizable and stronger dispersion forces. In practice, within a family of similar drugs or molecules, those with higher molar mass may have stronger dispersion forces, making them less volatile and more likely to be liquids or solids at room temperature. Boiling point trends often reflect dispersion force strength. For example, in noble gases, helium is less than neon, which is less than argon, which is less than krypton, and less than xenon. Each step down the periodic table adds electrons, increasing polarizability and boiling point. In a clinical setting, this explains why some medical gases are liquid at room temp under modest pressure. They have stronger intermolecular forces. This figure compares noble gas boiling points. The heavier the atom, the higher the boiling point due to stronger dispersion forces. It's the same principle in organic molecules. Larger hydrocarbons, like in lipid-soluble drugs, have stronger dispersion forces, influencing how they distribute in fatty tissues. Dipole-dipole forces occur in polar molecules, ones with a permanent separation of charge. The positive end of one molecule is attracted to the negative end of another. These forces are stronger than dispersion forces alone, so polar molecules generally have higher boiling and melting points than nonpolar molecules of similar mass. In nursing, this affects drug solubility. Polar drugs dissolve better in water, also polar because dipole-dipole interactions occur between drug and solvent molecules. In formaldehyde, CH2O, oxygen is more electronegative than carbon, so electrons are pulled toward oxygen, creating a permanent dipole. The positive side of one molecule aligns with the negative side of another, increasing attractions. This same principle helps explain protein folding in the body. Polar side chains can align and interact via dipole-dipole attractions. Two molecules with similar mass but different polarity will have very different boiling melting points because polar molecules add dipole-dipole forces on top of dispersion forces. Example, acetone polar versus propane nonpolar. Acetone boils much higher. Clinically, think of IV fluids. Polar molecules like glucose mix easily with water, while nonpolar lipids require emulsifiers to stay dispersed. Mini NCLEX style question. A nurse is preparing two IV medications. One is highly polar, the other is nonpolar. Which statement is most accurate? A. Both will dissolve easily in water. B. The polar drug will dissolve better in lipid solutions. C. The nonpolar drug will require a lipid-based carrier for IV administration. D. Nonpolar drugs always have lower boiling points than polar drugs. Correct answer C. Rationale: nonpolar drugs don't mix well with polar solvents like water. They often require lipid-based carriers or emulsions for IV delivery. Miscibility is a liquid's ability to mix with another liquid without separating into two layers. Rule, like dissolves like polar liquids mix with polar liquids, nonpolar with nonpolar. Example, water, polar, and pentane, nonpolar, do not mix. Water and ethanol, both polar, do. Clinically, this matters for IV fluids and medication compatibility. A polar drug will dissolve in polar IV fluids, like D5W, but not in nonpolar lipid emulsions unless formulated that way. This slide shows real-world examples. Oil, nonpolar, and vinegar, polar water-based, separate. An oil spill sits on seawater. This is why you can't wash greasy hands with plain water. You need soap to bridge polar and non-polar worlds. Nursing angle. In parenteral nutrition, lipids are kept emulsified so they don't separate from aqueous components in the bag or tubing. To know if a molecule is polar, you need to ask two questions. 1, does it have polar bonds? Look at electronegativity differences. 2, do the polar bonds add up to a net dipole? Check the 3D geometry. If both are yes, it's polar, which means it has dipole-dipole forces in addition to dispersion forces. In healthcare, polarity determines how a drug distributes. Polar drugs stay in watery compartments such as blood plasma. Nonpolar drugs accumulate in fatty tissue. CO2, polar bonds between carbon and oxygen, but linear shape so the dipoles cancel, which means it is a nonpolar molecule. CH2-Kel2, polar bonds. Carbon-chlorine bond is more polar than carbon-hydrogen bond. With a tetrahedral shape, dipoles don't cancel, so it is a polar molecule. CH4, nearly nonpolar bonds, carbon and hydrogen, with a symmetrical tetrahedron shape, so it is nonpolar. For nurses, understanding polarity helps you predict drug solubility and why some drugs need special carriers or solvents. Hydrogen bonding is a special, stronger type of dipole-dipole force. It happens when hydrogen is covalently bonded to a very electronegative atom, such as fluorine, oxygen, or nitrogen, and is attracted to an electronegative atom on another molecule. Examples include H2O, HF, and H3. These bonds are strong because the small size of H allows molecules to get close. Clinical tie-in, hydrogen bonding affects drug receptor binding, protein folding, and water's high boiling point, which is essential for maintaining liquid water in the body. In HF, the hydrogen atom is strongly attracted to the fluorine atom of a neighboring molecule. This is why HF boils at a much higher temperature than expected for such a small molecule. In biology, similar strong hydrogen bonds stabilize the shapes of proteins and nucleic acids. Methanol has OH groups, so it forms hydrogen bonds with other methanol molecules. Each hydrogen on the OH group can interact with an oxygen on another molecule. In medicine, alcohol's hydrogen bonding with water explains why it mixes completely with water, which is important for preparing antiseptic solutions. This slide compares two compounds with similar molar mass, one with hydrogen bonding and one without. The one with hydrogen bonding has much higher boiling melting points because more energy is needed to break these strong intermolecular forces. In healthcare, hydrogen bonding is why water stays liquid at body temperature and doesn't evaporate away, vital for hydration and homeostasis. Water has two OH bonds, so each molecule can form multiple hydrogen bonds with others. This network makes water's boiling point, 100 degrees Celsius, very high for such a small molecule, 18 grams per mole. In the body, this strong hydrogen bonding is why water is liquid at physiological temperatures, why it's such a good solvent for polar and ionic substances, and why it supports life processes. It's also why ice is less dense than liquid water. Hydrogen bonding locks molecules into an open structure when frozen, causing expansion. Mini NCLEX style question. A nurse is diluting a lipid-soluble medication for IV administration. Which solution would best dissolve the drug? A. D5W, 5% dextrose in water. B. 0.9% sodium chloride in water. C. Lipid emulsion, intralipid. D. Sterile water. Correct answer C. Rationale: lipid-soluble, nonpolar drugs dissolve best in nonpolar solvents. Lipid emulsions are designed for this purpose. D5W sodium chloride solution and sterile water are polar and will not dissolve nonpolar drugs effectively. Ion dipole forces. Ion dipole forces occur when charged ions interact with polar molecules. Example: in a sodium chloride solution, sodium ions are attracted to the oxygen side of water molecules, partial negative, and chlorine ions are attracted to the hydrogen side, partial positive. These are stronger than hydrogen bonds because ions carry full charges. Clinical relevance. This is the chemistry behind IV electrolyte solutions. When we dissolve sodium chloride in sterile water for infusion, ion dipole interactions keep sodium and chloride ions stably dispersed. It's also key in drug absorption. Ionic drugs dissolve well in polar body fluids due to ion-dipole forces. This summary table shows dispersion forces are the weakest and it is present in all molecules. Dipole-dipole forces are only present in polar molecules. Hydrogen bonds are strong and present in bonds between H and F, O, and N. Ion-dipole forces are the strongest in this group, present between ions and polar molecules. For nurses, knowing this helps predict solubility. Polar ionic drugs dissolve in polar solvents. Nonpolar drugs require lipid carriers. DNA is made of nucleotides, each with one of 4 nitrogenous bases, adenine A, thymine T, cytosine C, or guanine G. The 2 DNA strands form a double helix, held together by hydrogen bonds between complementary bases. A pairs with T using 2 hydrogen bonds. C pairs with G using 3 hydrogen bonds. These specific pairings are critical for accurate DNA replication. Clinically, this is why genetic mutations can happen if hydrogen bonding patterns are disrupted, for example, by certain chemotherapy agents or radiation. Adenine always hydrogen bonds with thymine, cytosine with guanine. This specificity is due to the number and arrangement of hydrogen bond donors and acceptors in each base. If a base is damaged or replaced, hydrogen bonding may no longer align correctly, leading to replication errors. In nursing, this underpins why certain genetic disorders occur and why targeted drugs, like some antivirals, are designed to mimic bases and interfere with hydrogen bonding. When a cell divides, the DNA double helix unzips by breaking hydrogen bonds between strands. Each half then serves as a template for building a new complementary strand, with new bases forming hydrogen bonds to their matches. Clinically, this process is why rapid cell division, like in cancer, is vulnerable to drugs that disrupt hydrogen bonding or base pairing. Each nucleotide has 3 parts, a phosphate group, a sugar, deoxyribose, and a nitrogenous base, A, T, C, or G. The sugar-phosphate backbone forms the rails of the DNA ladder, and the bases form the rungs through hydrogen bonding. For nurses, understanding this is crucial in fields like oncology, genetics, and molecular diagnostics. This illustration shows multiple hydrogen bonds between complementary bases, giving DNA both stability and flexibility. The bonds are strong enough to keep the strands together under normal conditions, but weak enough to be broken during replication or transcription. This balance is vital. Too strong and DNA couldn't unzip, too weak and it would fall apart spontaneously. Mini NCLEX style question. A nurse educator explains how certain chemotherapy agents work by disrupting hydrogen bonds between DNA base pairs. Which effect would this have on the cell? A. Prevent formation of the sugar-phosphate backbone. B. Inhibit separation of DNA strands for replication. C. Increase the solubility of DNA in water. D. Strengthen base pairing to prevent transcription. Correct answer, B. Rationale: hydrogen bonds hold the 2 DNA strands together. Breaking or altering them improperly can prevent the strands from separating correctly during replication, halting cell division. Solids can be crystalline, meaning atoms or molecules are arranged in a regular repeating pattern, or amorphous, meaning no long-range order. Crystalline solids fall into 3 main categories. Molecular solids, composed of molecules. Ionic solids, composed of cations and anions. Atomic solids, composed of individual atoms. In nursing, understanding these categories matters because solid form affects drug stability, dissolution, and bioavailability. For example, some medications are amorphous to dissolve faster, while others are crystalline for stability. This slide is a classification chart showing examples of each type. For example, ice and dry ice are molecular solids. Sodium chloride is an ionic solid. Diamond and metals are atomic solids. In pharmaceuticals, crystalline solids tend to be more stable and have predictable shelf lives, while amorphous forms may dissolve faster but can degrade quicker. Molecular solids consist of molecules held together by intermolecular forces, dispersion, dipole-dipole, or hydrogen bonding. Examples: ice, H2O, hydrogen bonding; dry ice, CO2, dispersion forces. These tend to have low to moderately low melting points. In healthcare, many drugs in tablet form are molecular solids. Their melting points affect how they're processed, stored, and delivered. For example, keeping certain antibiotics refrigerated prevents them from melting or degrading. Ionic solids are made of positive and negative ions in a lattice. Example, table salt, NaCl, calcium fluoride, CaF2. They are held together by ionic bonds much stronger than intermolecular forces, so they have very high melting points. Clinically, think about electrolyte supplements. Solid NaCl is very stable, but once dissolved in water, IV fluids, ion dipole forces keep the ions dispersed and available for physiological use. Ionic bonds make these solids extremely stable and hard to melt. NaCl melts at 801 degrees Celsius. Compare that to a molecular solid like carbon disulfide, which melts at 110 degrees Celsius. For nurses, precipitation of ionic solids in IV lines is a safety concern. If two incompatible IV solutions mix and form a solid, the patient could be harmed if the precipitate is infused. Atomic solids are made of individual atoms, not molecules or ions. They can be further divided into covalent atomic solids, atoms held together by covalent bonds, non-bonding atomic solids, atoms held together only by dispersion forces, and metallic atomic solids, atoms held together by metallic bonding. For nursing, this classification is less about bedside care and more about medical devices and equipment. For example, metallic solids, stainless steel, for surgical instruments. This slide shows the breakdown with examples. Covalent atomic diamond, non-bonding atomic solid xenon, metallic atomic iron silver. Understanding this helps with material selection in medical tools. You wouldn't make a surgical blade out of xenon, but you would out of a strong metallic solid. These are like one giant molecule. In diamond, each carbon is covalently bonded to 4 others in a tetrahedral pattern. It has extremely high melting points. For example, diamond, approximately 3,800 degrees Celsius. Clinically, covalent atomic solids are used in specialized medical tools. For example, diamond-coated surgical blades for microsurgery. Here you see diamond's rigid 3-dimensional network. This is why it's the hardest natural material known. In healthcare, diamond-tipped tools allow for extremely precise cuts, such as in ophthalmic surgery. These are held together only by dispersion forces, very weak, so they have very low melting points. Example, solid xenon melts at negative 112 degrees Celsius. They're rare in clinical settings, but the principle is relevant in cryogenic storage. Xenon and other noble gases can be used in specialized anesthesia research and imaging. In metallic solids, positive metal ions sit in a sea of delocalized electrons. This makes metals conductive, malleable, and sometimes very strong. In nursing, metallic solids are everywhere: stainless steel instruments, titanium implants, and conductive materials in monitoring equipment. This slide shows the electron C model. The free-moving electrons explain why metals conduct electricity and heat so well. Clinically, conduction is important in devices like defibrillator paddles or ECG leads, which rely on metals to transmit electrical signals efficiently. Mini NCLEX style question. A nurse is preparing an IV calcium infusion. Which property of calcium salts, ionic solids, is most important to monitor during preparation? A. They melt easily at room temperature. B. They have low solubility in water and may precipitate. C. They are metallic solids and conduct electricity in solid form. D. They sublimate easily during storage. Correct answer, B. Rationale. Many calcium salts have low water solubility. If they precipitate in IV lines, it can cause embolism risk. Ionic solids do not melt easily, are not metallic, and generally do not sublime at normal conditions. Water is unusual. With a molar mass of only 18.02 grams per mole, it should be a gas at room temperature, but it's liquid. Reason? Strong hydrogen bonding between water molecules. For nurses, this is critical. Water's high boiling point and liquid stability mean it can function as the body's universal solvent, carrying nutrients, electrolytes, and waste products. Water's bent shape and polar OH bonds give it a significant dipole moment. Each molecule can hydrogen bond with others, making water an excellent solvent for polar and ionic compounds. In healthcare, this is why IV fluids can dissolve salts, sugars, and many drugs, and why water can transport them throughout the body. Everywhere we find liquid water, we find life. In the body, water maintains temperature, transports nutrients, lubricates joints, and supports cellular processes. For nurses, dehydration assessment is central. Changes in water balance affect nearly every organ system. Unlike most liquids, water expands when it freezes. This is because hydrogen bonds lock molecules into an open hexagonal structure in ice, making it less dense than liquid water, so ice floats. Clinically, this matters in cryopreservation. Ice expansion can rupture cells and tissues, which is why controlled rate freezing and cryoprotectants are used in preserving organs, embryos, and blood products. When water in cells freezes, it expands, often rupturing membranes. This is why frostbite destroys tissue. The ice crystals damage cell structure. Industrial flash freezing of foods minimizes crystal growth by freezing so quickly that water molecules can't form the expanded ice lattice, a principle also applied in rapid cryopreservation techniques for medical samples. Poor water quality can cause infectious diseases such as cholera, dysentery, hepatitis, and typhoid. In developed countries, drinking water is treated to kill microorganisms, often by chlorination or filtration. For nurses, patient education on safe water practices is key, especially for immunocompromised patients who may be more susceptible to waterborne infections. Water can also be contaminated with chemical pollutants, industrial waste, pesticides, heavy metals like lead and mercury, nitrates from fertilizers. Unlike biological contaminants, many chemicals aren't removed by boiling. Clinical relevance. Chronic exposure can cause neurological, developmental, and systemic toxicity, as in lead poisoning from contaminated drinking water. Let's pull the big ideas together and see how they connect to nursing practice. Liquids and solids exist because of intermolecular forces. Without them, everything would be gas. The strength of these forces determines whether a substance is a solid, liquid, or gas at a given temperature, and affects boiling, melting points, vapor pressure, and solubility. Phase changes, melting, freezing, evaporation, condensation, sublimation, are all about balancing thermal energy and intermolecular forces. Each phase change absorbs or releases heat, which is why these concepts matter in thermoregulation, cooling with ice packs, sweating, preventing hypothermia, warming patients. Quick recap of the three major intermolecular forces. Dispersion forces, weakest present in all molecules and atoms, caused by temporary fluctuations in electron distribution. Dipole-dipole forces occur in polar molecules due to permanent partial charges. Hydrogen bonds, strong special case of dipole-dipole, involving H bonded to N, O, or F. In nursing, these forces explain why some drugs dissolve in water and others in lipids, why proteins fold the way they do, and why certain IV medications can or cannot be mixed in the same bag. Molecular solids, low to moderate melting points held by dispersion, dipole-dipole, or hydrogen bonding, for example, ice sucrose. Ionic solids, high melting points held by strong electrostatic attraction between ions, for example, NaCl. Atomic solids, covalent network, diamond, extremely hard, high melting points. Non-bonding, solid xenon, weak dispersion forces, low melting points. Metallic, iron, variable melting points, good conductors. Clinical tie-in, solid form influences medication stability, dissolution rate, and storage requirements. For example, certain crystalline drugs are less soluble and absorb more slowly, impacting dosing. By the end of this unit, you should be able to use heat of vaporization and heat of fusion in calculations. Determine types of intermolecular forces in a compound. Predict melting and boiling points based on intermolecular forces. Why this matters in nursing. Fluid and temperature regulation in patients involves phase changes, evaporation, condensation, melting, freezing, and energy transfer. Predicting solubility and compatibility of medications relies on knowing molecular polarity and intermolecular forces. Understanding why certain materials behave as they do in clinical settings, from IV fluids to surgical instruments, improves patient safety and care outcomes. Final NCLEX-style wrap-up question. A patient is receiving 2 IV medications. One is polar and water-soluble, the other is nonpolar and lipid-soluble. Which nursing action is safest? A. Mix both drugs in the same saline IV bag. B. Use separate lines or compatible emulsions for administration. C. Dilute the lipid-soluble drug with sterile water before mixing. D. Add extra saline to increase miscibility. Correct answer, B. Rationale: polar and nonpolar drugs are generally incompatible in the same aqueous IV solution. Using separate lines or a lipid emulsion for the nonpolar drug prevents precipitation or separation that could harm the patient.